and welcome back. This is part 2 of rational applications, or applications of rational equations. If you haven't watched the first part, make sure you go back and do that now, because we're about to jump into some pretty complicated problems. So let's jump right in. So for example, this problem here. So a kayaker spends an afternoon paddling on a river. Now they travel 3 miles upstream and 3 miles downstream in a total of 4 hours. In still water, they travel an average speed of 2 miles per hour. Based off this information, what is the speed of the current? Now, you're going to see problems like this quite often. You'll see problems that talk about distance, rate, and time, like 2 trains leaving a station and yada, yada, yada. You're going to see these problems a lot. And when we set them up, the first thing I like to do is I like to talk about what the variable is. What are we trying to solve for? Well, in this problem, we're trying to solve for the speed of the current. So I'm going to call my variable C and call it speed of the current. Now, in this, we're given a distance, we're kind of given a rate, and we're also given time. So we're going to be using our distance formula, which is distance is equal to rate times time. And when we cover these types of problems, I like to stay organized with a distance, rate, and time table. And notice that it's split up between 2 differences. The differences is traveling upstream versus downstream. So that's how we're going to split up our table. So we're going to have a distance, a rate, and a time for upstream and downstream. Now, if we go through this problem and really pick apart all the information, we see that they traveled 3 miles upstream and 3 miles downstream. So I'm going to fill in the distance portion of this table with 3 for both upstream and downstream since they traveled the exact same distance. Now, the rate is a little bit more tricky. They're telling us that in still water, they travel 2 miles an hour. So that means without a current. So if there was no current, this kayaker would be able to kayak at 2 miles an hour. So that's going to be part of our rate. However, they're in a river and this river has a current. So we have to think about, does the current help or hurt the kayaker's progress? And this actually kind of stems from the last video where if 2 people were helping each other's progress, we would add their rates. And if they were hurting each other's progress, we would subtract their rates. It's the same exact idea here. Well, if you're swimming or kayaking or doing anything upstream, you're fighting against the current. The current is not helping you, it is hurting you. So what we are going to do is we're going to take the speed of the kayaker in still water and subtract the speed of the current. Because if you think about it, the kayaker can go 2 miles an hour kayaking, but they're going against that current, so we're going to take away the current speed from the kayaker. And then conversely, if you're going downstream, the current's actually helping you, right? If you're traveling downstream, that current is actually pushing you, it is helping you, it's aiding you, so we are going to add their rates. And remember, we don't know the speed of the current. That is the value of C. Now, the next part is a little bit trickier when we talk about time. Well, they gave us one really big key piece of information in regards to time, and it's that they traveled 3 miles upstream and 3 miles downstream in 4 hours. So if we take how long they spent going upstream and add it to how long they spent going downstream, that should be equal to 4 hours. Do not think that it's 2 hours each and evenly split it, because that shouldn't make sense. It should take longer for them to travel upstream than downstream, right? Because they're fighting the current instead of getting help from the current. So we know that time upstream plus time downstream is going to be equal to 4. The only thing is we don't actually know what the time of each portion is. However, we can kind of manipulate our our distance equation to get us time is equal to distance over rate. If we just go ahead and solve this equation for time there, we can go ahead and figure that out. And from there, I can make a rational expression for time. So time upstream will be the rate, the distance, which was 3, over the rate, which was 2 minus C. So there's our expression for time. And then we can do the exact same thing for downstream. Our distance, our rate, divide them. There's our expression for time. And from there, we can set up our equation. Time upstream is 3 over 2 minus C. Time downstream is 3 over 2 plus C. We add these two together, and that should be equal to 4 hours. And from here, this should be pretty straightforward. It's solving a rational equation. So we would first go ahead and find the least common denominator and multiply each side of the equation by the least common denominator, which would be 2 minus c and 2 plus c. And then we can cancel out all the fractions using that clearing the fractions method to be left with a quadratic equation, which we should be able to solve from Algebra 1. So go ahead and distribute, get everything on one side, and factor. Actually, in this case, you can solve by using square roots since the c's, the linear term, actually cancels out. And when we take the square root of each side, remember that it has to be plus or minus. So that's how we get c is equal to plus or minus 1. Now, we're dealing with an actual application here, an actual situation. So sometimes when we get two answers, only one of them is going to make sense. Speed cannot be negative, right? Speed cannot be negative. The current can't be traveling negative 1 mile per hour, so we must get rid of that answer and instead only take the positive, which is positive 1, which tells us the speed of the current is 1 mile per hour. And that would be our final answer. Now, like I said, these ones are a little bit more challenging, a little bit trickier. They take a lot of practice. So I want to cover two more examples. They're going to be slightly different, but have kind of a similar tone to them. So let's go ahead and take a look at our next problem. Okay, let's take a look at this one. A motorboat can travel 20 miles per hour in still water. So once again, we're having some sort of rate in still water. Now, if the boat can travel 3 miles downstream in the same time it takes to travel 2 miles upstream, then what is the rate of the river's current? Basically, what's the speed of the current once again? So that is exactly what we are solving for. So I'm going to go ahead and say c is equal to the speed of rate. That should be speed of the river's current. Let me go ahead and fix that. There we go. Got it fixed. Now, once again, distance is equal to rate times time, and we're being given information such as that, so we should probably set up a table. And once again, it's being split up between upstream and downstream. I know that the previous problem was like this, but a lot of them are going to have somewhat of a similar setup, okay? Now, in this one, they're giving us two different distances, so we need to make sure we place them accordingly. We can travel 3 miles downstream, so I put 3 in a distance column for downstream, and 2 miles upstream. So those are the distances that we are given. From there, we got to talk about rate. Well, once again, they're telling us that we're going with and against the current for downstream and upstream, and they're telling us the speed of the boat in still water is 20 miles per hour. So if we're going upstream, the boat is fighting the current once again, so we're taking the boat speed and we're subtracting from it the current speed, which gets us 20 minus c. For downstream, the current's actually helping the boat, so we're going to take the boat speed and add the current speed since it is helping it. Now, time is going to be a little bit different. Now, a huge piece of information is that it said it can travel 3 miles downstream in the same time it takes to travel 2 miles upstream, which means the times are equal. So time upstream is going to be equal to time downstream. So once again, I can set up an expression for time and call it distance over rate. So upstream's time is going to be the expression 2 over 20 minus c, and downstream's time is going to be 3 over 20 plus c. But the real big takeaway here is that they're telling us the same time, which means the times are equal. So we're going to set these times equal to one another and solve. And this is one that's actually a little bit easier to solve because this is just cross multiplication, as a lot of you guys probably remember it as. So I would cross multiply 2 times 20 plus c, 3 times 20 minus c, set those equal to each other, distribute, and solve. So I would go ahead and move all the pieces around, solve for c to get c is equal to 4. And that answer should make sense, and it is the correct answer. Remember, we can't have a negative speed, but this is not negative, so 4 miles per hour is our final answer. Now, let's cover one more example. This one's going to ramp it up just a little bit and make sure that you are taking good notes. Let's go ahead and take a look at that final example now. All right, so this last one's going to be a little bit more challenging. So Susan drove 1,500 miles to Daytona Beach for spring break. On the way back, she averaged 10 miles per hour less. And on the drive back, it took 5 hours longer. So not only did she drive a slower speed, it took her longer to get back, and that should make sense since she's driving a little bit slower. Now we want to find her average speed on the way to Daytona Beach when she was traveling faster and got there quicker. Now this one's going to be a little bit more challenging. First thing I'm going to do is set up our variable. I'm going to say S is the speed on the way to Daytona. That's what we're solving for. And we're going to go ahead and set up our table. So we set up our table, once again, distance, rate, and time. And in this particular problem, we have two differences, going to Daytona and coming back from Daytona. So that's where we're going to split it up. Now distance is the same, right? We went to Daytona, we came back from Daytona, is 1,500 miles in each direction. Now the rest of this is going to get a little bit trickier. Now, on the way back, she did 10 miles per hour less. The only thing is we don't know the distance, or excuse me, the rate going to Daytona. But that's actually what we're solving for. Ooh, I got two variables. I'm calling it X in the table. I'm calling it S up top. Let me go ahead and change that S to X to make this make a little bit more sense. There we go. Definitely don't want to be changing your variable up midway through the problem. My apologies for that. So we don't know the speed going to Daytona. That's actually what we're trying to solve for. That's actually our variable X. So I'm going to go ahead and put X in that column. And now what we do know is that when she was coming back from Daytona, she actually went 10 miles an hour less. So I'm going to take that speed going to Daytona and take away 10 from it. So X minus 10. Now from there, we should be able to look at this piece of information. It took 5 hours longer to come back than to go there. So this one actually trips up a lot of people. For example, let's say it took me 5 hours longer to go to the store than to go to the gym. Those times are definitely not equal, right? It took me 5 hours longer to go to the store than the gym. So what I would end up doing is take, and there's kind of a couple different ways you can set this up. One way is to get these to set equal to one another. I would take the shorter of the two times, add the extra time to it, which would be 5 in this case, and set it equal to the slower time. So in essence, since it took 5 hours longer to come back from Daytona, if I add 5 hours to how long it took to go to Daytona, then those times would end up being equal to one another. So time going to Daytona plus those 5 hours is going to be equal to the time coming back from Daytona. Now, you can also think about it the other way and have time going to Daytona is equal to time coming back from, and then minus 5, or you can actually subtract the two times coming and times going, and set those equal to 5, okay? So there's a couple different ways we can tackle this. But regardless, we should know that time is once again equal to distance over rate. So we get 1,500 over X for the time expression going to Daytona. And then we're going to get 1,500 over X minus 10 as the time expression coming back from Daytona. And now I can go ahead and set up my equation. Well, I'm putting my time going to Daytona plus 5 is equal to the time coming back from Daytona. So I'm plugging in those particular rational expressions. And now I have an equation that I can go ahead and solve. So I find the least common denominator, which would be X and an X minus 10. And I multiply everything through by that least common denominator. Remember, that's called clearing a fraction, so all the fractions are going to end up canceling, and it leaves me with a much easier equation to solve. Now, the numbers are going to be a little bit bigger, yes, but once you get to this point, you might notice that they have a greatest common factor of 5, so you can divide each side by 5, or you can go straight to like just using the quadratic formula if you really want. I like factoring, so I went ahead and factored this. So I got X minus 60 and X plus 50, which got me answers of 60 and negative 50. Now, once again, we got two answers, but only one of them should make sense. Speed cannot be negative. We're trying to find the speed on the way going to Daytona. That definitely can't be negative 50 miles an hour. So what I got to do is I got to get rid of that negative 50, and 60 would be the only correct answer. So she was averaging 60 miles an hour going to Daytona, and that's what we were asked to find. If we were also asked to find how fast she was going from Daytona, just plug it in. 60 minus 10, 50 miles an hour. Okay, and that would be our final answer. And that's rational expressions. Now, there are different types of these types of rational expressions. You can see them in a slightly different way, but just know that a lot of them are going to boil down to setting up some sort of table like this and just reading the problem very, very carefully and using the information that is given to you. I hope this was helpful because I know this is a very challenging topic, but I hope this video was helpful. If there's any questions at all, please feel free to reach out and let me know. Otherwise, I look forward to seeing you guys in the next video.